So let's now talk about vector addition and subtraction. So the key thing with vector addition and subtraction is that we're going to be performing it component by component. And so what that means is we're going to look at, if we're talking about Cartesian coordinates, we're going to look at our x component for each vector, we're going to look at then our y component for each vector, and we're going to consider it sort of one component at a time. So in order to sort of illustrate that a little clearer, let's consider two vectors. Let's consider vector A, which has an ax component in the x direction, an ay component in the y direction, and an az component in our z direction, and a second vector b, which has bx in our x direction, by in our y direction, and bz in our z direction. So notice again I'm using angle brackets as opposed to the parentheses that are used in the book. So let's say we want to find some vector c, which is equal to the addition of a and b. So what we're going to do is we're going to focus on our x components first. So we can say, to write it in a slightly different notation, we can say that this is our ax plus bx in our x direction. So I'm going to write that as unit vector x. Because remember, we could write either of these as ax in our unit vector of x direction plus ay times uy plus az times uz, and we could do a similar thing for vector b. So now that we've done our x component, we would look then at our y component. So we would come here and we can say that this is ay plus by in our y direction. And then finally, we would look at our z component, or z components rather, and we would have az plus bz in our z direction. And of course, we could write this c in sort of the simplified notation with the angle brackets as well. So we could have in parentheses here ax plus bx, comma, ay plus by, comma, az plus bz, and then close our angle brackets. So we could represent it that way. So that's how we would do our basic addition, so pretty simple. So now what if we were wanting to subtract some vectors? So let's say we had d, which is equal to a minus b. How would we do that? Well, it turns out what we can do is really we can still just do addition. So instead of saying a minus b, we can say d equals a plus -1 times b. And of course that's the same thing. So basically we can just use the same technique we did with our addition here to find c in order to do subtraction. Another sort of useful way is to do this graphically. So some people I know are better at using numbers and variables. Some people are better at seeing it graphically. So whichever way works better for you, feel free to do that. But we can also visualize these properties graphically. So let's look at how that looks. So what we're going to do, there's a couple different techniques. I'm going to show one here and then I'll mention where another one is in the book. So we can visualize graphically with something called our head to tail rule. And that's what we're going to show here in a second. You can also do something called the parallelogram rule, which personally I think is a little more complicated than it needs to be. But if that makes more sense to you, you can look at that on page 7 in the textbook. So if we're going to do this graphically, let's consider our vectors graphically. So just kind of arbitrarily writing our vectors, let's say our a vector looks something like this, and let's say our b vector is something like this. So if we wanted to find c, which remember was a plus b, so let's say c, which is a plus b, what we do is we would write out our a. So here's our a, and then at our ending point of a, we're going to start with b, so we get something that looks like this. And so we then connect in our c vector between our starting point and our ending point. And so it's going in the direction from start to end. So this would be start, this would be end, so our c is going in sort of this up and to the right direction in this case. So that would be what our c looks like. We could also do the same thing graphically for subtraction. So for instance, if we wanted to do d, which was a minus b, So remember we had D is A minus B, but we said really that's plus a negative B. So first what we do is we just flip this B around. So we would say our negative B actually looks like this. So it's just in the opposite direction. So we do that same head to tail rule. So we have A, and then our plus negative B, we have something like this. And then we do the same rule of going from our start point to our end point. So in this case, we would see our vector D looks something like this. So that's how we could look at this graphically. So the last thing I want to talk about in this video is some properties for our addition and subtraction. So properties for addition and subtraction. So our first one is commutative. And so for addition, we have, let's see, let me do a couple different columns here, because we're going to have addition and then we're also going to talk about sort of simple scalar multiplication. So addition and multiplication. We're going to come back and talk about vector multiplication a little later on, but cumulative property for addition is basically the order doesn't matter. So we have A plus B is equal to B plus A, so either order is fine, we get the same result. For multiplication, if we have some scalar value k being multiplied by a vector, k times A, that's the same as if we have A times our scalar value k. The second property is associative property. And so what our associative property says is it doesn't really matter which sequence we do first. So let's say we have three things that are being added together, three vectors. So A plus the quantity of B plus C, where all three are vectors. Well, we could add A and B first and then add C later, and that's going to give us the same thing. In terms of our multiplication, if we have two scalar values, K and L, so let's say we do L times our vector A and then multiply that by K, well, that's the same thing if we did any other order. So for example, K times L and then multiplied that by A. So the last property here is our distributive property. And so that's if we have some scalar being multiplied by the sum of vectors A and B, we can just distribute that and say, well, that's equal to our scalar K times our vector A plus our scalar K times our vector B. And so again, let me just write explicitly that in those equations above, our K and our L are scalar quantities. So hopefully, again, that was pretty basic, pretty easy review, but we're going to look at some examples a little later on to get some practice. And as always, if you have questions, please don't hesitate to let me know.